Well, thank you very much. I've actually been a Delaware professor for 30 years, believe it or not, and I've been gone from Delaware for 22. So you're not really looking at a young man here, but nevertheless, it's good to be back after the long time. And I also wanted to tell you that I'm coming at this from a different perspective. I'm not a public health person. I'm a bioclimatologist. So my work has been from the climate side of all of this, trying to model climate to understand how it affects human health, which is different than what some of you are doing. So today what I want to do is discuss a system that we're using to try to evaluate the dangers of heat waves based on human health outcomes, which is different than most of them that base it on just meteorological thresholds. And then to talk at the end about some of the ways we can literally mitigate the problems of heat, particularly in urban areas where most of these deaths occur. So that's going to be the content of my talk today, and we'll see how it goes. One of the other things I want to emphasize is that none of this work is done or can you accomplish much without interdisciplinary action. And I'm going to hammer away at that this whole talk. These are some of the organizations that we're working with: the California Office of Environmental Health Hazard Assessment, right down to the 3M Corporation. And you might wonder how people who make Post-it notes can have anything to do with this kind of work, and hopefully you will at the end. So what are our goals here? We have a Delaware Valley Heat Health Coordination Group. Matter of fact, some of my members are sitting right back here. There's at least 3 of them, along with our Delaware ex-state climatologist who just retired, an old friend of mine, Dan Leathers. So we have a very powerful group right here in the Delaware Valley that can work on this. So we want to work with them and coordinate with them and increase awareness about the dangers of heat on human health. One of the ways to do this is to improve regional warning systems. And we have been working for years because we don't think they're proper. Often the thresholds are the same, whether you're in Duluth, Minnesota or Dallas, Texas. And we need to make a lot of changes to that. And that's one of the things that we're working on right now. But also, no health system is any good without proper intervention. What do you do if an emergency is called? And there are some places like Philadelphia, for example, which is way ahead of the game, and they've been doing lots for years. And there are other places, I remember in New Orleans, where an excessive heat warning is called and almost nothing is done other than to tell the people on the radio and TV announcing that there's a heat warning. So we're going to talk a bit about that. Internationally, this has really spread, and I'm thrilled that we've been part of this. Climate Resilience for All is a nonprofit that has just been developed, partly to develop heat warning systems for India based on human health. And as many of you know, especially outdoor workers in India are incredibly stressed during temperatures that often exceed 100 degrees. Something has to be done about that. And so we're trying to develop not only a warning system online, but also an app that people can look immediately at and know they've got to do something and relax and rest. So we've done work now with Greece. We have a system operating all through Greece. I'll show you how that works. In Spain, and a couple of US cities. And Gavin Newsom a year ago signed a law in California, AB 2238, which is designed to develop heat health warning systems for the entire state of California. Amazingly, we got called as climate lead on this. We aren't even in California, so we are honored. But everyone I work with is in California. And much like the world today, we meet on Zoom. I've never met the people that I'm working with, much like the Delaware Valley group I met just now. It's a very interesting world we live in. But we are developing this. Our first job was to homogenize all of California's climates. So my team has just finished dividing California up into 35 climate districts, but I'm getting off the point here. The idea is you need a compendium of people to work together to do this. Working in major cities is most important, and we continue to emphasize, especially in India now, we're starting with Ahmedabad, very large city of 6 or 8 million in northwestern India, which is much more dangerous there than it is in tropical India because of the irregularity of the heat. And I want to talk about that as well later on. And we're also evaluating our system since we actually estimate the number of people who are going to die from the heat. We don't show the people this, but it's online on a password protected site. We don't want them to know that we expect, imagine the Philadelphia Inquirer saying 26 people expected to die from the heat tomorrow. So basically that's for the health practitioners, but we do have those numbers and we can compare them against real mortality to see if, in fact, our systems are working properly, and if not, how we can correct them. So I guess we all know why we're concerned about heat. By far, the leading weather-related cause of death in the United States, and I mean by far, it's greater than all other weather-related causes involved. Lightning, blizzards, hurricanes, you name them, they don't equal an average year of heat. In America, between 1,500 and 2,000 people die annually of heat on average, but the variation is huge. You can have a cool summer where almost no one dies, and then you can have a summer where 8,000 or 10,000 people die. And so the range is so big that some years heat is one of the major killers in the United States. Of course, I will not talk about this very much because we have an actual medical expert talking after me, Lisa, who will talk about the reasons people die of heat. But when we do our work, use all-cause mortality. We don't just pick out heat-related deaths or heat stroke. They grossly underestimate the number of people who die of the heat because, quite honestly, many heart attack victims, stroke victims, respiratory failure victims, they're dying of the heat, but they're never recognized as such. But if you graph them on a daily basis through a time series, they spike during heat waves. So they must be included, but they never are because the medical examiner never knows if that particular heart attack victim died because of the heat. One of the most important things to get out of this today, if you get anything out of it, is that climate variability is much more important than just the actual level of heat in terms of damaging human health. That's why more people die of heat in Toronto than Phoenix. Because people in Phoenix, first of all, know what they're doing. Why? Because it's hot every day. The urban structure is designed for heat. Those buildings, the swamp coolers, all of the things they use in Phoenix, they're smart. They know what to do during a heat wave. Where do people die? In London, in Paris, during an occasional excessive heat wave, because they don't know what to do. There's not much air conditioning. There's little green space in those European cities. The whole urban structure is not designed to deal with heat. So we find that I live in South Florida. By the way, we didn't flood out. I heard someone mention it before. It was a bad rainstorm, but we're still alive and standing. But nevertheless, many less people die of heat in South Florida than they do up here. Every day is the same in the summer. Uncomfortable, granted, but every day is basically the same. So we're used to it. And also other things about heat are important. Extended heat events. People can survive one day, maybe even two. But when you get to 3 or more days in a row of excessive heat, that's when people start dying. Overnight minimum temperature comes out as more important than the maximum temperature. If you're in an unair-conditioned environment and it doesn't cool off at night, that extended heat period is very, very dangerous for people. So there are other little clues about heat that are important. And by the way, early season heat waves are much more dangerous than the exact same level heat wave late in the season. So same meteorology in June and September, many more are going to die in June. Why? First of all, there's an adaptation problem. It's the first heat wave of the summer or the second heat wave. And second, and this is odd, but you kill off the susceptibles in the early heat waves, and there are less available to die later on. Now, our system is not based on comfort. It's based on health response. So that would mean that that early season heat wave would require much more intervention than the same meteorological heat wave late in the season. We're sorry you're uncomfortable, but if you're not going to get sick and die, it's not worthy of spending millions of dollars in a city to go and do a lot of work. So this is a very important feature, and we call it mortality displacement. You've seen this all the time. When there was COVID, very few people died in the summer during the heat waves because COVID killed them beforehand. And so often our models are off. Our models don't know that it was COVID beforehand. And those are some of the inaccuracies that we have to deal with. So how bad is it? What is the problem like? This is just a trace of 1979 through 1995. I've shown this slide for years, but it is so dramatic that I always have to show it. There are deaths per 100,000 in Chicago, and on average, about 3 people per 100,000 die in Chicago every day. Chicago's metropolitan area has about 6 million people, okay? Now, you could see every single heat wave. This is all-cause mortality. Every single one stands out. Now, you might say, well, that little blip over there, let's see if I can get this to work. Oops, I'm going the wrong way. I made a mistake, actually. So let's forget about the little pointer. In any case, you can see where those little blips are. And you might say, well, those are just little tiny blips. Are they? So if you go from 3 to 5 per 100,000, and there are 6 million people in the Chicago metropolitan area, that's 2 per 100,000 extra. Multiply that by 60. That's 120. That little blip is a day with 120 extra deaths, okay? And then, of course, you have the granddaddy of them all in 1995, which was so off the charts. Books have been written on by it. The mayor was not reelected because of poor policy during that heat wave. And now we're up to, what, 13? Let's just say that's 13. That's 10 per 100,000 over the baseline. You're talking about 600 deaths on one of those days, and that's why they had refrigerated trucks lined up in Chicago to store the bodies. There were just too many to deal with during that heat event. So what do we do about it? You get a consortium together. We have our Delaware Valley Consortium, but it's not the only one that I'm working with. I'm working very closely with the state of Wisconsin. I actually have 3 University of Wisconsin PhD students who work with me on this consortium. And we have an alliance of groups, as you could see. Part of it is this University Alliance, which is the University of Wisconsin and the city of Madison. We have the Dane County, Public Health. Everyone is in this. We're all working together on trying to lessen heat-related deaths in Madison and in Milwaukee, and we are working on it. One of our systems is running there. One of the ways we approach this is differently. This is one thing that a climatologist would do. We are synoptic climatologists. That is, we look at the whole picture of weather. We don't just look at temperature and humidity and rainfall. We put every day into an air mass type. And I can tell you that many of my University of Delaware students did this for their dissertation and have developed really sophisticated air mass analyses. One is called the spatial synoptic classification, which puts every day into those different air mass types: DM, DP, DT. D is dry, P is polar, T is tropical. DT is a dangerous air mass. That's a dry tropical air mass that comes from the deserts or descends the Appalachian Mountains and causes 100-degree temperatures here and in Philadelphia. The other bad one is MT plus, moist tropical plus. You can guess what that is. A Bermuda high is offshore. It's pumping hot, humid air from the Caribbean and from the southern Atlantic. Hot, humid, often not as hot as dry tropical because there's clouds and sometimes thunderstorms, but the overnight temperatures are higher in that. So we track the mortality of these air masses, and you could see immediately that on an average DT day, this is from Milwaukee, we have almost 3 extra deaths on those days. Considering that about 15 people die on average in Milwaukee County a day, you're talking about a 20% increase in that particular case on average. Some days are worse, some days aren't so bad. For MT plus, not quite as bad, but these are what we do. We pinpoint those air masses to define a heat event, not just temperature, because it's the whole. Some of them have poor air quality. There's a whole agglomeration of things within those air masses that cause the problem. And then we come up with another thing that we really basically recently discovered. We didn't discover it. It has been used in Australia for the last 5 or 6 years, and it's our favorite new climate index. It's called the Nairn-Fawcett Excessive Heat Factor. Well, Nairn and Fawcett were the developers of this. And the way it works is that it looks at 3-day periods. And if those 3-day periods exceed the 95th percentile in apparent temperature is the temperature humidity combination and the way it feels to us, then something happens. We look at that 3-day period and see how much above the 95th percentile it is. That's what that excess heat circle is. And then we multiply it by the apparent temperature the 30 days prior. Why? Because if the 30 days prior were cool, it's going to be a different thing than if the 30 days prior were hot. So that's one of the reasons a May heat wave is so bad. But also, if you had no heat during the summer and you get a bad one in August, that would be considered bad as well. So I give you an example. Assume a mean 3-day apparent temperature is 29 degrees centigrade. That's 84 Fahrenheit. And the 95th percentile is 25 degrees. Assume that the mean apparent temperature the preceding 30 days was 20 degrees. So it's 29, what it was for those 3 days, minus 25, the 95th percentile, times 29 minus 20, what it was the 30 days preceding, and you get a value of 36. 36 excess heat factor points. Let's assume the month before was cooler. It was only 18 degrees and not 20. When you multiply that out, it's 29 minus 25 times 29 minus 18. The number goes up. So that's the way the excess heat factor works. So a combination of our synoptic air mass categorization and this rather simple unit, which we really think deals with adaptation to heat, comprises most of what we do. We can make it much more complicated. You could put in solar radiation and all kinds, but then it's not usable. You need values, meteorological values that are relatively simple to fork. We're looking ahead. What are the forecasts? If you use solar radiation, you don't have good solar radiation forecasts ahead. So we need these variables that are relatively simple to make these things work. So in our evaluation, we look at the previous 30 days weather, we look at the 3 days of the heat wave, and then we estimate mortality for the next 7 days using our model that I'll show you in a second, because the next 7 days you see lag increases in mortality for not only the day of the heat wave, but for 5 or 6 days afterward. So we look at 7 days ahead of time. Of course, there's a distance decay. The further out you go, the less the problem. So here's 3 examples. We can look at Milwaukee and Madison since we worked on this. We have divided heat waves into actually 3 categories and a hot day. Level 0 is a hot day. But much like hurricanes, we are now defining heat waves and ranking them. Matter of fact, in Seville, Spain, they're naming them like hurricanes, and I'll talk about that in a second. But we have these level 0, 1, 2, and 3. If you look at that graph, you see the excessive heat factor, what we just talked about, on the x-axis, and the average increase in mortality in Milwaukee County on the y-axis. There's a remarkable relationship with very narrow error bars. Those gray bars are the error bars. And so I put 2 dots on there. The first dot shows Madison and Milwaukee for, in that case, let's see, it's level 2, where you have a 9% increase in mortality with 90 excess heat factor points, and level 3, the higher dot, where you have a 15% increase in mortality for 111 heat value points. We've done this for all the cities that we work with, and the slopes are rather different. So for example, there's Milwaukee County. I just showed you that one. This is an adjacent set of counties, suburban, less poor people, less population density. Look at what happens. You can see the relationship is poorer and the error bars are wider using the same scheme. Now, our question always is, which of these relationships do we use in a heat warning system? Well, we're not alarmists, but we want to use the one for the most sensitive population, not the one that's less sensitive. And that's basically what we do in this case. All right, I don't want to leave out our area. So we've done this for our area as well. Philadelphia County on the right looks something like Milwaukee, doesn't it? Not surprising. And by the way, at 40 or 50 excess heat points, we're looking at a relative risk of 1.4. That means that the average increase in all-cause mortality at that heat level is 40%, 1.4. It's phenomenal how sensitive this is. All right. Montgomery County, rich people generally, spacious, green, air conditioning. We didn't find a thing. Newcastle County, somewhere in the middle. Now, of course, if we did Wilmington specifically, I'm sure we would have had a different value than if we used all of Newcastle County. But although the error bars are wide, we have found a relationship here. One of the reasons we use county is because that's the easiest data to get in mortality. The CDC makes available to the public county-wide data for the whole United States. So we have everyone who's died in the US for the last 30 years by county. To get the census tract data or the zip code level data, that's a challenge, as Lisa can tell you, because we try to do this all the time. So that's why we're using this for right now. But clearly we could do a better job in Newcastle County. But this is what we have for now. So this is our system. This is what it looks like. It's up right now. This is the Philadelphia heat ranking system. Just a few days ago, it's on a password protected website. You see PHL forecast issued 6/17/24 at 13:41 hours, 1:41 in the afternoon. That was just before the heat event. And this is the information provided. First of all, the categories, the level 0, hot day occurring, be careful. But as you move up to a level 3, which is the most dangerous, usually the most dangerous 10% of all heat waves, you've got a real problem. And there is June 17th, the day of the forecast. And then we get prospective data from the Weather Service for the next 7 days if we wanted, but it's not very accurate 7 days out. They actually do it hourly. So we go out 4 days, 5 days at the most, because the accuracy goes down. And that's enough time for stakeholders to start doing something about it. Notice for June 20th and 21st, it was a level 3. The excess heat factor was predicted to be 35.1, an estimated increase of all-cause mortality in Philadelphia of 12.7%, using the relationship I just showed you on the slide before. And then even worse, June 21st, 32.1%. How do we know where to divide them? Well, the first city we did was trimodal. We saw frequencies of heat waves that were trimodal, so we said, let's start with 3. I'll be honest with you, we've seen all different types of modes from there on in, but we stuck with 3, hot day and then 3, because we think that's enough classes to separate the not so bad heat waves from the really terrible heat waves. And then we usually have a kind of a 60-30-10 distribution. 60% are level 1, 30% are level 2, and the worst 10% are level 3. A little arbitrary, but I think it works well. And that allows, instead of just saying we have an excessive heat warning, now you have this divided up into levels so that the intervention people can target what they need to do based upon the intensity of the heat event. I told you we do this in Greece. It's been great working with international people. Greece has incredible mortality data and weather data. So we work with the National Observatory of Greece, and they provided data for us for the 7 biggest cities in Greece. And so this map appears every day publicly on their website on Meteo Greece. I could give you the website and you could look it up. There it is, by the way. You could look it up and you could see it right now if you went onto your phone. And they update this every day and have forecasts in advance. By the way, that box in the upper right-hand corner says today and tomorrow and the day after. So you click ahead and you could see them. And that's the pyramid. 1 means no problem. 2 means a hot day. And then 3, 4, and 5 are our level 1, 2s, and 3s. So it's been fun to work with them. We are now getting started on filling in the whole map of Greece, not just the big cities. And we're going to work on that next. But Seville has probably been the cornerstone of the work we've done. It's the hottest city in Europe. Getting over 100 is a piece of cake in Seville. That it's really not bad at all. And so what we've done is we've looked at all the days from 1995 to 2022 that had any excessive heat factor points. And there they are. You can see the levels 1, 2, and 3. Over 300 summer days had some excessive heat factor points. We had 54 events of 3 or more days, which we designate as a heat wave. That averages to about 12 days per summer, but notice it's not 12 days per summer. Some years we have, 24? Other years we have 1 or 0. That's the whole nature of meteorology, that it goes in those kinds of cycles, making it unpredictable. And by the way, someone said we're going to have I think you said maybe we're going to have a bad hurricane year. I wouldn't bet my life on it. They're as good as they can be, but it's almost impossible to forecast, just like it is impossible to forecast these. Even with El Nino and La Nina and Southern Oscillation and all the things you hear, it's still very difficult. So the highest heat wave year had 24, the lowest had 0. So how do we rank a day? How do we figure out what its rank should be in terms of 1, 2, and 3? This is a 19-day heat wave that happened in Seville right here. It was from July 28th, 03 to August 15th. That was the actual mortality on those days. Right next to it, the actual all-cause mortality, on average about 15 or 16 people die in Seville every day. There were days there in the 30s, double the average mortality in Seville. Even as aware of the hot weather as Seville is, they doubled on several days their mortality. The third column is our prediction based on our model. I didn't show you the curve for Seville, but we have a curve just like that for Seville. That's the third column. And we were certainly far from exact. I mean, clearly there are many other things that kill people besides heat, but we didn't do badly. I mean, we isolated the worst periods pretty well. And then what we did is designated them level 0, 1, 2, and 3 days. How do we do the whole heat wave? Where you see the third column, the one that's colored, the total mortality increase for those 19 days, if you added up those numbers, is 903%. We divide that by the 19 heat wave days that you had, and you get an average of mortality increase for the whole event of 48%. Well, that's a level 3. I mean, an average of 48% for the heat wave is very, very high. That's the number used. And then we categorized all 54 events that happened in Seville. We do this for every city that we work with. Anything above, now we didn't do the 60, 30, 10 rule for Seville. It's too darn hot and too deadly. So you can see there's a lot of category 3 events, 12 events, more than category 2. How can you call anything that has a 30% or higher increase in mortality anything but a category 3? So we lowered our standard and made more category 3 days because of that. And you can see every one of those, there's the 19-day heat wave, the fourth one down in the upper left, 7/28/03, 19, that was the 48%. It wasn't even the worst. It was the longest, but it wasn't the worst. So that's how we categorize those. So how did we do? We compared our system to the existing Spanish heat system, which was based on meteorology only, AEMET, A-E-M-E-T, which is the Spanish government's system, much like that's the National Weather Service of Spain. Okay, they called events from 1995 to 2022, wherever you see the black line, that's when they called events. We called all the others. Now, by the way, a system that calls more events isn't necessarily better. So I don't want you to think that, oh, look at that, we called more. But let's check just the category 3. We know those were days that a lot of people died. Look at how many their system missed. They missed one in 96, a long one. They missed one in 2000, the dark red. They missed another one in 2010. They missed another one in 2015, and they missed another one in 2022. They missed category 3 events because it was based on meteorology only, and they didn't consider the health outcome by developing that algorithm. So guess what? Now they're using this, and we've been getting press all over the place. Our system, our ranking system is all over the news in Spain and even in America. Most places don't want to name heat waves. The National Weather Service will never name a heat wave like hurricanes. They just won't do it. But in Seville, we named every heat wave that was category 2 or 3 backwards. We started with Z after talking to the government about it. So the first heat wave was Zoe, and it was terrible. And we had press all over the place. So we're very excited. They're still using the system. we now transport all the code that was on a university computer in America. They're now running it themselves. So are the Greeks. So will the Indians when we finally finish with that. We don't want to run these for all the cities. We just don't have the manpower to do it. So we move it over. So anyway, that's the system aspect of all of this. Now what I wanted to do is end with a little bit of discussion on how we respond to these situations when you get them. So let's talk a little bit about product solutions. This is where 3M comes in because they make much more than Post-it notes. They make materials that are very, very important for cooling cities. For example, the Industrial Mineral Products Division makes a granule that goes into the roofing of houses that quadruples the reflectivity of the roof. So in other words, the average roof, I think, reflects somewhere between 7 and 10% of radiation that hits it. You put these granules in, you've upped it to 30 to 40%, okay? And that means less air conditioning costs. I mean, it's all kinds of good things that happen because of this. You have more reflectivity off the roof. These roofing granules are literally a brilliant product. And of course, 3M, they're a for-profit company. This is not like some nonprofit like Climate Resilience for All. All right, so they make a profit. They're developing products that are very, very important. And so they invite customers, roofing companies, to add this to their shingles, and they hired us to determine how many lives could be saved if, let's say, half the roofs had these materials. They also do it for those flat industrial roofs. Remember when you fly into an airport, you always see all those warehouse buildings with the roofs, the flat roofs. They make up a big proportion of urban areas, and they work with them as well. So, by the way, they now make a pollution-absorbing granule that absorbs nitrous oxides, which is the manufacture of ozone in the long run, which we don't want in the atmosphere. And then when it rains, the granules release the nitrous oxides and they fertilize your lawn. Now, come on, I just listened to this and I say, what a brilliant, that's why I love 3M, the fact that they come up with things like this. So this is a 3M slide. Air conditioning and refrigeration consume 25% of the electricity generated worldwide. We're talking about big numbers. 7% of global greenhouse gas emissions are from cooling. It's a big number. 600 trillion liters of fresh water are used in cooling systems. And finally, 6 times the growth in electricity used by cooling by 2050. You're talking about a major, major issue here. So here's one of these collaboratives, and this was one of the favorite things I've done in my entire career. It took me to be as old as I am now to be part of the Los Angeles Urban Cooling Collaborative, which I co-founded with a professor from UCLA. There's me, applied climatologist, but we're only part of this whole group. This project was funded by the Forest Service because we also evaluated what increase in tree vegetation in the urban areas would do to cities. And it was a combination of universities. Tree People is a nonprofit that deals with planting trees in LA. Climate Resolve is another nonprofit. The Global Cool Cities Alliance rates these roofs to tell you how cool they are. So it was a great collaboration. And we looked at different scenarios based on increasing tree canopy and roof albedo. And I had a modeler from Arizona State University, a brilliant man named Dr. David Saylor, who models cities if you change the surface of the cities. So he was my prime modeler. And we used 4 what we call prescriptions: low tree canopy, high albedo, high and low, and finally the pie in the sky 4, which was high tree canopy and high albedo. And you can read in the bottom how we increase them, but just take my word for it, we increase them significantly, so you don't have to bother reading that right now. We chose 4 heat waves to evaluate. And by the way, the beauty of the synoptic classification is that not all heat waves are created equal. The DT are the hot, dry desert heat waves. They react differently than the MT plus heat wave. So we took one that was hot and humid in LA, all MT plus days. We took one that was a mixture, MT plus and DT. We took one that wasn't that bad of a heat wave. And then we took one that was very hot. You may have heard of the Santa Ana. This is where the winds blow from the east in Los Angeles County, and Los Angeles County is sloping downward as you get closer to the coast, and it goes up to 105 in Santa Monica, which is a place where it's supposed to be cool all the time, and they happen occasionally. We found one of those. So this is what David Saylor did. He modeled the city. This happens to be a scenario 1, low tree cover, high reflectance for part of the heat wave in August 26, 2029. And he modeled the city 3 times a day if we met that scenario. The blue is the amount of cooling that would happen in the city. The darker the blue, clearly, the more cooling. And the arrows show the winds because he models the winds as well at the surface. So usually in the middle of the day, when you want it to do the most, that's when you have the worst problem. And you could see it right there. By late afternoon, because of the winds, this begins to dissipate. But also the problem is solved over the poorest parts of Los Angeles, which are the darkest blue areas. That's where Watts is, and the inner cities of Los Angeles, Compton. That's where the problem is reduced. So we divided LA into 18 homogeneous, social homogeneous areas. Rich, widespread out areas like Beverly Hills, or the Simi Valley, number 18, which is light residential, compared to 5 and 6 and 11, which are places where we have densely populated minority populations. And sure enough, using this particular scenario, in this case, number 4, you could see where the darkest green occurred. There were some places we couldn't understand. 10 came out with nothing, but you could divide the city homogeneously and see which areas would benefit from the use of high tree canopy and these reflective shingles as well. 16 is a very hot area in the San Fernando Valley. So even though that's not a poor area, we weren't surprised, but you could see the distribution. Now, the real final thing I want to talk about here is that what does this do to climate change? We found that on average, using scenario 1, we can cool LA County by 1.1 degrees centigrade. Scenario 4, the pie in the sky, 1.7 degrees centigrade. What does that do to climate change? If you use a business as usual model, you can delay climate change with prescription 4 by 43 years, because that's when the model says we're going to reach 1.7 degree increase in temperature. So you could delay climate change by 43 years. Who knows what you could develop in those 43 years to solve the problem? Now, if you use a model that is some mitigation, we have less effluent, we determine a way to make less emissions or whatever, you're going to do even better. That's probably more realistic because it's going to take longer to reach those temperatures. So at least in the urban areas, you can delay climate change by using these products. And this is why I'm all for their use. So to conclude, I love interdisciplinary collaboratives. I think they've increased awareness. I don't know much about public health. I need people like Lisa to teach it to me. And so this is really important that you have these collaboratives. There are a variety of policy options to choose from and cooling scenarios to use, but we have the technology today to cool these cities. Today. And I always say, because there's a lot of global warming skeptics out there, instead of arguing, oh my God, in 50 years, we're going to triple the number of people who die, I say it is a major problem today. And the skeptics can't argue that, can they? It is a major problem today. And that's the way I always look at it. And so we can improve this. We'd like to do some of this in Delaware. So we're talking to people, and we've given presentations, thanks to Pat and others, to one person who may actually be your next governor. I don't know much about Delaware politics, but in any case, we've been talking about this to leaders, and we hope that they making a system like this for the state and also developing ways of mitigating the problem part of their agenda. So thanks for your attention.
Actually, my question is sort of slightly related, which is when you're looking at deaths, you're basically taking everybody, not specific causes of death, correct?
No specific causes, but you do use specific demographics. So we have from the CDC, the data includes, we can divide it down by cause of death. I mean, we include accidents, suicides, everything is included in there. But we can also look at elderly, 65 and older, infants, less than one. Everyone's race and ethnicity is listed. So we can segregate, let's say, African Americans, Hispanics, if we want, and so on. So we can segregate we can segregate male and female. So we have certain groups that we can segregate. Constantly when we do this, and I can show you this in other tables, constantly the elderly are always by far per capita the most vulnerable. Then come next are generally African-American males that come out very, very high. And then you have other groups that come on down. The least vulnerable are always Asians. And we don't know enough about, I can't even define why that is the case. I'm sure we could probably come up with reasons. One of the reasons one of my friends came up with is that among Asian families, especially in China, Korea, and Japan, elderly people live at home with the families much more than they do in America. And that maybe because of this, the parents can keep an eye on them, because many of the people that die of heat are elderly who live alone in urban areas. That could be, it's a total speculative statement. So that could be totally wrong, but we can divide it up. The point is, though, that we do keep them generally together other than for our own research purposes, because the results still come out strongly. And we do believe that they represent the general population best. But you can develop a system for nursing homes if you want, or with any other group based on using 65 and older, or any other designation of the demographics.
So my follow-up though is that it's not a mechanistic model. Basically, you have the data and you're fitting your results to those data. And one of the things that as an entomologist is that early season temperature allows development of mosquito populations earlier on, which, because it's a cumulative growth for multi-generational populations, you may end up with much larger populations later in the season, when you can have mortality because you had more transmission of, say, West Nile virus, which does kill more elderly people. So I'm just trying to figure out what are some of the mechanisms. I mean, I understand why you're putting together a heuristic model, but I was just in my head, I was just trying to figure out that there's clearly other phenomena underlying all this, like you said, also the greenery, and there's
absolutely. We have not ultimately solved the problem. What we have done is developed a way to make an accurate warning system that's better than what we have right now, especially when they're based on meteorology. Now, you may know this, the Weather Service has just produced what's called heat risk. Have any of you heard of heat risk? It is a new heat evaluation system that's going to rank heat waves, and it does include health. And we've seen heat risk and we've looked into it, but they divide the country into like 6 health regions. So if you're from Oregon, Washington, or California, you're in the same health region. What we do is do the health for the local urban area, so we have a local response. So we think that our way of capturing health, and I hope there's no National Weather Service person in here to damn me for saying this, but we think that our way of segregating health effects is better because it's based on the local response rather than on the generalized one. Thank you.
Thank you. I think this heat risk index is going to be very helpful. I have a question, or I'd like you to clarify your comment about the increasing albedo and planting the trees, potentially changing climate. Can you clarify microclimate changes versus global climate changes? I think that's an important distinction.
It's not going to affect global climate change. If I implied that we're going to solve the climate change problem by doing this, that's certainly not what I meant to say. You are going to change the climate of the localized area, of the localized urban area. LA, like and we have it down to districts. Those districts had to be, the way we defined them, we had social scientists from Cal State Northridge do it. The homogeneous districts had to have at least 300,000 people, because we developed a different algorithm for each of those districts in LA. And they had to be homogeneous in terms of housing, demographics, and so on. But please understand, we're not solving the global climate change problem. And when I say we're going to delay climate change, that's for that urban area, not for the globe. So I'm glad you asked that question, because if it came off that I said Oh yeah, we're solving global warming. I certainly didn't mean to come off that way.
If only that were true, right?
Yes, exactly. Thank you for bringing that up.
Just a quick question in reference to rural America. Have you actually looked at rural America and tried to apply these to the farming communities where you do have these small microclimates due to plant growth and extreme humidity?
There is one article on rural area in Ohio put out by my ex-grad student here at Delaware, Dr. Scott Sheridan. And he did find a strong rural relationship to mortality as well, even though there's no urban heat island effect. But this is going to change. We just gave a presentation to the National Council of American Indians at their conference in Cherokee, North Carolina. One of my Wisconsin grad students gave that. And they are very interested in developing systems for Native American tribal communities. That will be our first real experiment for rural America. It's not going to be easy though, because they're very sparsely populated for very large areas. And what we need are dense populated areas in the same climate zone to make this work. So let's take the Navajo Nation, one of them that we're interested in. If you look at a map, it is the entire northeast fifth of Arizona. That's the Navajo Nation. Maybe a couple of 100,000 people live there. So how do you do a system for an area like that? And this is going to be a challenge. So the NCAI, the National Council of American Indians, said that they will provide us, if we do this, with personalized mortality data that have been collected by the tribal communities, which are different than the ones collected by CDC, which includes everyone who lives in whatever county it happens to be in. So hopefully for 25, we'll have our first pilot for an Indian nation. And if we do, we'll see if this works. I will be honest with you, we've never done one for a largely rural area. We just have done one study that Scott had done before. That's a very good question.
Thank you, Dr. Kalkstein, for this excellent presentation. I just wanted to ask you if there are folks from Delaware here, if the state of Delaware were to decide on a system like that, a warning system like that, how long does it take to create a system? And just to give an idea to people here, if a system was created, how it could be utilized, where does that system live, how long, and if you could just give out a little bit more details.
Sure. Thanks, Shweta. Sounds like I almost planted that question that Shweta just gave. But obviously, that's a good question. It takes about 3 months for us to do it, to collect the data and to develop. And if we did one for Delaware, we'd have a separate system and an algorithm for Newcastle County, and then an algorithm for the 2 downstate counties, if we did it. Obviously, the summer's gone, but we would have it up and running by next summer without a doubt. But there's much more than just developing a system like this. It would be just like the one I showed you for the cities up here. It would be exactly like that. And on the page, you'd click on Newcastle County and get Newcastle County's forecast, and then Kent and Sussex. And luckily, Delaware's flat, so we don't have a variety of climates like we would have if you do California, which is why we have 35 climate zones in the state of California. The idea here is that we've got to get a consortium, and that we already have the rudiments of, but to include more of you in this room and to have people who are policy people as well. So what I would like to have, if we can do it, and I know you all, Pat and Shweta and Lisa, we'd like to have a group of 8 or 10 people where we would align ourselves to developing something like this for Delaware, but also policy people. Okay, you have a climatologist, you have public health, you've got APHA, you've got interested medical people. We also need policy people. The state climatologist should be on board, and Dan knows about this anyway, as does his successor. So we need that. The total cost for a system in Delaware would be $35,000. For a running system on the website like this, it would cost $35,000. It's cheap. We would maintain it for the first 2 years on our university servers. And then it gets transferred to the state of Delaware. This is the way we do it with Greece and with all the other cities that we use. And of course, we would troubleshoot. This includes all troubleshooting. So I think it's a worthwhile thing. What it doesn't include, though, are the extra money spent for intervention. And of course, the state would have to put that in mind too. If you have more elaborate intervention techniques for each of the 3 levels, that's going to be another cost to the state. But this system could be up and running by summer 25 with no trouble at all. So, okay, thank you so much. I really appreciate it.